Hello friends, welcome to CSES group 2018 control system problems from electrical engineering optional we will be looking now, and I am bringing the Matlab result of these examples such that we can easily verify that our answers are correct or not. Okay, so let's start with these questions. Question number 1C of 2018 was, there was one open loop transfer function given to you which is mentioned here, and we were supposed to determine the following. The first is point of intersection of asymptotes with the real axis. Second is point of intersection of root locus with the imaginary axis and the value of k at this point. Okay, so I have already solved a complete question based upon root locus for 2019 that I'll be sharing a link here. You please check in the top of this right side of the slide. Now we are only looking for these 2 points, so we'll focus on these two. For that, we first want to know that how many poles and zeros are there in the question. Okay, so now you can see the denominator is having of order 3. That means there are 3 poles in the given system. One has origin, that is s equal to 0. The other two are at -4 and -5, and you don't have any numerator polynomial. That means there is no 0 in this system. And the intersection of asymptote is given by summation p minus summation z divided by p minus z, where summation p is sum of all the poles, summation z is obviously sum of all the zeros, and this p shows the count of pole and this z goes for the count of zeros. So if you do so, you will find -4 minus 5 divided by 3, which comes out to be -3 divided by -9 divided by 3, which is -3. Okay, that means what? There are 3 asymptotes which are meeting at point on the real axis which is at -3. So first point is point of intersection of asymptote with the real axis. Okay, so this we have solved. So at -3 all the 3 asymptotes will intersect the real axis. Okay, this is what the first part. Let us understand what is given in this S-plane diagram also. So I have drawn this real imaginary part. This is real part and this is imaginary. Okay, and we have 3 poles. One it has origin, so this is first pole. The other is at -4 here, and the third is at -5. Okay, we also should know that where the root locus will start and where it will end. So you have to remember the thumb rule that the root locus always starts from open loop pole and terminates at open loop 0. If there is no 0, then they will terminate somewhere at infinity. Now if you find you don't have any pole in the right side of this origin, hence the root locus must start from this origin and move towards the -4. Okay, from -4 there will start a new root locus which will go towards the origin. Similarly, from -5 also there will start a new root locus which will go in this direction towards the negative infinity. Again, this explanation I have already given in my previous video, that is 2019 video. I will not go for that again. You can refer to the 2019 video for the control system. Now we need to know that these 2 points or these 2 root locus, when they will coincide, how they will move. Okay, which one? This is starting from origin and starting from -4, because obviously they are moving towards each other, hence they must coincide somewhere and they should go to somewhere else, and how they will move, that will be decided by the asymptotes. Okay, and obviously the asymptotes also will intersect at the real axis, and that point is being asked in the question, and which is -3. Okay, and we can also find out the angle of these asymptotes, which is given by 2k plus 1 into 180 divided by p minus z. Okay, so k goes from 0, 1 and 2. If you substitute these k values, you will find 60, 180 and 300. So from this point, considering this as a reference, if you draw 60-degree angle, let me remove these annotations. Okay, if you have the angle of 60 degree from here, there will be a root locus asymptote which is going in this direction. Then 180 is this one, and then you have 300 which is here. Okay, so in this way you can easily identify how these asymptotes will move. So first part of this question is done. Now the second part is point of intersection of root locus with the imaginary axis and the value of k at this point. For this you need to solve the characteristic equation, because we are looking for the roots when they will be having only imaginary part. Okay, and that is possible when one of the element of this first column of the Routh Hurwitz is 0. Based upon the value of k, we will identify how it will be done. So we will form the characteristic equation using the GSHS which is given to you. Please remember guys, the characteristic equation is given by 1 plus GH is equals to 0. Okay, so that's what I am doing here. 1 plus GH is equals to 0. If you do so, you will get this expression. Okay, so this is your characteristic equation. Now you need to use the Routh Hurwitz table. So this is what the Routh Hurwitz criteria. This is multiplication of 9 with 20, that is 180, then k with 1, so 180 minus k divided by 9. Okay, so first term will be here, this will be 0, and again the cross multiplication in this way it will go. Okay, so finally you will end up with k at the end. Now the point of important is here. Okay, so this we will try to equate with 0, and if you equate it 0, that's I am writing here, you will find that k comes out to be 180. That means what? When k value is 180, one of the element of the first column will become 0, which shows that for that point of k, the roots will lie on the imaginary axis. Okay, and what will be the value of roots? That can be identified by forming the auxiliary equation from this row. Okay, let me remove again the annotation. Okay, so we need to form the auxiliary equation for this row, and substituting the value of k is 180. Okay, so that's what I am forming here. 9s square plus k, where k is 180, is equals to 0. You will find s square is equals to minus 20, which is s is equals to plus minus j under root 20, which comes out to be j 4.47. Okay, with plus minus sign obviously. So this is what the point on the root locus where they will intersect the imaginary axis, and the corresponding value of k is 180. We can verify the given result using Matlab. I have written a simple 3 lines Matlab code, and we got the same result exact points, that is 4.47j plus minus for the value of imaginary roots. Okay, that is given in the next slide. So you can see here this point goes with 4.45 or 4.47. Okay, these are the points or the roots value when the root locus will intersect the imaginary axis. Look at here guys, this is 0. Okay, so obviously this is the imaginary axis for you, and you can find the root locus which we have considered, that one will start from -5, the other will start from -4. The -4 root locus will move towards the origin, and the origin also there will start a new root locus. So exactly the same plot we are getting here. Look at here, from -5 there will start a new root locus, will go in this direction, and there will be intersection point, and one root locus finally will turn in this direction, the other root locus will finally turn in this direction. Okay, and they will terminate somewhere at k equal to infinity. Okay, so when k terminates to infinity or goes to very high value, then these root locus will also terminate somewhere in the infinity. Okay, that's what the root locus plot for given question. Similarly, in this direction also it will terminate somewhere in the infinity. That's it for this question. We'll go for the next. The next question is 3b. For the system whose open loop function is GSHS is given as this one, determine k which satisfies the following specification. Now what are the specification? Positional error coefficient or the constant must be greater than 2, and the gain margin must be greater than 3. Again, in the previous 2019 video, I have already discussed what is the gain margin and what is the phase margin using Nyquist criteria. So you can apply the same logic here also. So gain margin is at the phase crossover frequency. Okay, I have written the definition. Gain margin is the gain at phase crossover frequency. And what is phase crossover frequency? It is the frequency at which the phase is minus 180 degree. Okay, so what you have to do, you need to take this GSHS and segregate its real and imaginary part. Okay, so that's what I am doing, separating real and imaginary part by just multiplying with complex conjugate of the denominator in the numerator and denominator both sides. Okay, so what will happen, the denominator will terminate to a real part only, and you can simply segregate the real imaginary from the complete GSHS. Okay, so that's what I am doing here. You can verify easily that this the equation will turn to this value, and then separating the real imaginary part. So this is your imaginary part. Okay, so this part you need to equate with 0. Now why we are equating to 0? Because we need to find out the frequency for which the phase angle will turn to minus 180. Okay, so tan inverse of this value 180, basically tan of 180 is 0. That is why we are equating this, the complete imaginary part, to 0. Okay, so I'll write imaginary part will become 0. Then you can find the phase crossover frequency. So if you equate that to 0, this whole denominator term will vanish, and you will find that this k also will vanish, and you can easily find out the omega value, which comes out to be 4. That means for omega is equals to 4, the phase angle is minus 180 degree. Now we need to find out the gain at omega is equals to 4. So simply substitute this 4 at the real part. So this is your real part. So this part of the equation is your real part, considering the denominator also. So in this part you need to substitute this omega as 4, and which I have written here. For omega is equals to 4 you are substituting now. Okay, and you need to equate with the gain margin. Now what is the gain margin which is given here? Please remember, gain margin is identified by 20 log 1 upon gain. Again, I have explained everything in the previous 2019 lecture. So 1 upon a, where a is the gain for that point. Okay, so you need to equate with this. In the next slide I am solving that. So gain margin you want as 3. If a is the gain, then the gain margin can be expressed as 20 log of 1 upon a. You want 3, hence a must be less than or equal to 0.707. So gain must be less than 0.707 such that the gain margin will turn to greater than 3. Okay. Now what is the gain? Gain is identified by the previous equation when we are substituting the value of 4. Okay, again the k is unknown value, which basically we want to find out. So if you solve in this way, you will find, okay, let me correct it, this is less than or equal to, okay, so this is less than equal to sign will come. You will find that k turns out to be less than 70. Okay, that means what? When k is less than 70, you will find that the gain margin is greater than 3. Now the first criteria was the positional error constant must be greater than 2. Okay, so kp is identified as limit s tends to 0, limit s tends to 0, open loop transfer function, that is GSHS, must be greater than 2. That's what the criteria given in the question. GSHS is given by this equation. Okay, from the equation I am directly writing it. It is already given, and you need to substitute limit as s tending towards to 0. Okay, so this s will vanish, this s will vanish. You will find this 2 square, that is 4. Okay, and this is 3, so which I am writing here. So 4 into 3, that is 12. So k divided by 12 is greater than 2. That means k must be greater than 24. Okay, so you got the limit as k must lie between 24 to 70. If your k is lying between any of these two values, then obviously you can satisfy both of the criteria. Okay, what are those criteria which is given in the question? The positional error coefficient will be greater than 2 and the gain margin will be greater than 3. So I have considered k value is equals to 70, and I have plotted the bode curve or the bode plot of the given open loop transfer function. I have plotted this in the Matlab, and you can very well see this. For k is equals to 70, your system is stable obviously, and the gain margin comes out to be 3. It is written here, you can easily verify this. the gain margin is at the phase crossover frequency. This is gain margin and this is the phase crossover frequency. Now what is phase crossover frequency? It is the frequency at which the phase angle is minus 180. Okay, so corresponding, so this is at the frequency 3.39 or 4, and this frequency is coming as 4. At 4 it is comes out to be 3.1. okay, this can be easily verified since my pointer has moved little, so you cannot see the exact value of the frequency, but it lies in the same range. Okay, this can be easily verified here. So you can easily see that the gain margin we have attained as 3.1. Don't get confused guys, this frequency is at 4, and that's what we have already discussed, that at omega is equals to 4 the gain margin will be greater than 3 for k is greater than 70. Okay, so sorry, k is less than 70. So we have already verified and we satisfied both of the criteria of the given question. Next is, consider a unity feedback control system with forward path gain, that is gs is equals to 9 divided by s into s plus 1, and you need to find out the peak overshoot and ESS, that is steady state error for unit step and unit ramp input. Okay, so peak overshoot is given by this formula. We'll come to this. Before that we need to find out zeta. Okay, so this value we need to identify. This is identified by considering the standard form of the characteristic equation, which is given by s square plus 2 zeta omega ns plus omega n square. How you can do that? You need to go for this cs by rs is g upon 1 plus gshs, and this 1 plus gshs gives the standard form as this equation. So what you have to do, you have to compare this denominator with the standard form of the characteristic equation. You can easily find that 9 square is equals to omega square, okay, which I am writing here. That means omega is equals to 3, and 2 zeta omega n is equals to 1. Omega n you already got as 3, so 6 zeta is 1. That means zeta is equals to 1 upon 6, that is 0.1667. okay, now you can just use the maximum overshoot formula, which is given by e to the power minus zeta pi divided by under root 1 minus zeta square. Okay, so substitute the value of zeta and you will find that 58.8% of peak overshoot can be observed if this system is given. Now the second part is find out the steady state error for the unit step and unit ramp input. So steady state error is given by 1 upon 1 plus kp, where kp is identified using this or calculated using this formula. So I have substituted here, and you can very well recall that for the second order system the steady state error for unit step is always 0, and that's what we are able to see because the positional error coefficient comes out to be infinity, hence the steady state error is 0. Similarly for the ramp we can easily identify, it is given by 1 upon kv velocity error coefficient, and it is identified using this formula, limit s tends to 0 s into gshs. So this s will cancel out and you will end up with 9. So ESS for ramp input for the given system is 0.11. For this system the peak overshoot can be identified by plotting its transient response for the unit step input. So look at here guys, this is your input line. Okay, so maximum overshoot is defined by ct max minus ct infinity upon ct infinity. Okay, so this is what the peak overshoot formula is. Okay, this is also infinity. So ct infinity is 1 and ct max is easily identified using this plot, which is given as 1.58. okay, even you can easily verify in the Matlab, it can identify what is the overshoot, so it is also calculating it as 158.3. we also got 58% there, and you can even substitute in the formula in which we know, that is 1.58 minus 1 divided by 1. So this also comes out to be 58%. Okay, multiplying with the 100 will give you the 58%. And that's what we have identified, that 58% will be the peak overshoot for the given system when you are providing with the unit step function. Thank you guys. We'll see the second part, rest of the questions of 2018 next slide. Please subscribe the channel such that will give me the motivation to create more videos for you. Thank you. Jai Hind.